Hello everyone, good evening. I think voice is audible, right? Voice is audible, right? Thank you, thank you. In this class, we're going to concentrate more on subspace, right? So if there is time, I will touch rank also. So if not, I'll stop only on subspace. So subspace, I think it will go for 1 hour. So within 1 hour, 1 hour 20 minutes, I'll complete subspace. Uh, I'll see, right? Um, I'll decide whether to take rank today or tomorrow based on after completion of subspace, right? So within 1 hour 15 minutes, I will be completing subspace, right? Okay. So if you haven't watched the previous video, go through that because that is very important video because this is the continuation of the previous video, right? In the previous class, we have introduced the definition of vector space. The previous class, what we did, we introduced what is a group, and then I have given many examples of groups, and then I have defined what is field, and then I have given many examples of field, and then I have defined what is meant by vector space, and then we have seen some examples, right? Some examples of vector space, and then we did 3 problems in the previous class. So in this class, I'm going to introduce the definition of a subspace. So based on subspace, we will be doing some problems, right? We will be doing some problems, some 7 problems based on subspace, and then 3 theorems. So I'll define what is meant by subspace. Subspace. We'll be seeing 7 problems based on subspace, and then 3 theorems based on subspace. Right? Okay. So now it is 6:15. So I'll try to complete by 7:40. Right? That is, we're going to define subspace. We're going to see 7 problems on subspace, and then 3 theorems based on subspace. Right? Okay, so recall the definition of vector space, right? So I hope everyone have watched the previous class. So if not, kindly go through the previous class, right? Okay, so first what we'll do is we will define what is meant by subspace, right? Okay, okay, so the definition. So let V be the vector space. Let V be the vector space over a field F, right? You know what is meant by a vector space over a field F, right? You have non-empty set B and you have a field. This non-empty set B has to be an abelian group with respect to addition, and jointly they are satisfy 4 conditions, right? I hope you have seen previous class. Okay, so let B be the vector space over a field F, and let W be the subset of V. Let W be the subset of V. So that is W is a subset of V. So W is contained in V. See, for to be a vector space, we should have a field, and then we should have a set V, non-negative set V, and then we should have a field F. Now I'm taking a subset W of V, right? Let V be a vector space over a field F, and let W be the subset of V. Now this subset is going to be a subspace. As of now, this W is a subset because it is contained in V. This W is going to be a subspace if W itself a vector space over F. That's it. W is a subspace of V if W over F is a vector space. That's it. Right? That is, B of F is a vector space. You know, if it satisfies 5 conditions. B with respect to plus is an abelian group, and then 4 conditions. Alpha plus beta u is alpha u plus beta u. alpha times u plus v is alpha u plus beta v, alpha beta u same as alpha times beta u, 1 into u is equal to u, where 1 is the unity of f. So let V be the vector space over field F and let W be the subset of V. Then W is a subspace. W is a subspace of V if W itself, if W itself a vector space over F. I think you understand, right? See, to prove vector space, you will take V plus has to be an abelian group and four conditions. Now you take W. You take W plus has to be an abelian group. See, W plus has to be a vector space. That means you connect this and this. That's it. You connect this and this. So you W plus with respect to plus as an abelian group. You take two elements UV in W. So alpha times U plus V has to be in W. All these conditions itself, right? That's it. W over F is has to be a vector space, right? So let V be the vector space over a field F and let W be the subset of V. Then W is subspace of V, W itself vector space over F with the same operation, with the usual operation that is defined on V. See, whenever we need to prove vector space, we need to tell the addition and the scalar multiplication, right? So however you are defining in V, you define same as in W. However you are adding in V, you same add in W also with the same operation as in V. With addition and scalar multiplication, with addition and scalar multiplication as same as in B, right? See, whenever we need to prove subspace, it is not that easy, right? Again, we have to show that W over F is a vector space. That will be very hectic task, right? Now, I am going to give you the necessary and sufficient condition for a subspace to be a vector space. Very, very, very important. The necessary and sufficient condition. The necessary and the sufficient condition for W to be a subspace, for W to be a subspace of V is, I'm going to tell you two conditions, that's it. The necessary and sufficient condition for W to be a subspace of V is see, you have a set V and you have a set W is subset of V and then you have field F, right? I'm going to tell you two things. You take two elements W1 and W2 in W. The first condition is let you take two element W1 and W2 in W, then W1 plus W2 has to be in W. This is the first condition. You take two element in W, then sum has to be in W. And second thing is you take an alpha in field. You take an alpha in field. You take one W in W. This implies alpha times W1 has to be in W. Is it clear? You take two elements in W or instead of W and W2, see, let us say it is UV, right? It will be easy for you to understand because I don't want everything to be W. I don't want everything to be W. You take two elements U and V. You take two elements U and V in W. You take two elements. You take two elements U and V in W. Let U comma V belongs to W. Then U plus V belongs to W. You take an element alpha in F, you take one element in W, then alpha times U has to be in W. If these two conditions are satisfied, then automatically W will be a subspace, right? Very, very important. The necessary and sufficient condition for W to be a subspace of V over F, subspace of V of F over F is you take two elements in W, U plus V has to be in W. You take one alpha in field, you take one element in W, alpha U has to be in W. The scalar the scalar resulting scalar multiplying with scalar this u, this resulting product has to be in W. If that happens, then we say W is a subspace, right? So whenever we need to prove subspace, make sure that it is satisfying two. Or I can also combine these two, right? I can combine these two and I can write a single equation. Or you take alpha, beta in the field. You take two element in W. Then A alpha times U. Then alpha times U plus beta times V has to be W. This is a single stroke condition for subspace. Okay, I'm joining these two and writing this. The here says that the sum has to be in W. Here says that multiple of alpha from the field with U has to be in W. If I join these two conditions, then writing these two conditions in single line. You can either you can prove you take two element in W, you show U plus V in W. You take one alpha in field, then alpha times U has to be in W. You can either show two things for a subspace or you can show a single stroke. You take two element in the field, you take two element in W, you show that this linear combination alpha U plus beta V is also in W. Then we say that W is a subspace. Is it clear? See, you can show subspace in three ways. One is this W itself a vector space over a field F. That will be very very lengthy, right? Because you need to show W plus is an abelian group, and then you have to show four conditions. That is nine conditions you have to prove. It will lengthy. I'll tell you another way. You take two element in W, you show that sum U plus V is also in W. You take one element alpha in field, alpha times U is also W. You can show two things. Or you can show single thing that you take two element in field, you take two element in W, then you show that this element is also in W, then it will be a subspace, right? Or so you can do in three ways. The definition of subspace is clear. So whenever you need to prove subspace, you have to show you take two element uv in W, you prove u plus v is also in W and alpha u is also in W. Okay, so we'll move on to problems. So as I said, I'll be doing 7 problems and then 3 theorems based on subspace successfully completed. The set W of ordered triads, triplets A1, A2, 0, where A1, A2 belongs to field, the subspace of V3 over F. See V3, right? It is nothing but 3 tuples. V3 is nothing but 3 tuples. So it is same as R3. And over a field can be anything, but here will be field is we'll be talking about R, C, real number or complex number. Okay, so what is V is what? V consists of V is what? Your set V is your V3. V3 is nothing but R3. So V is nothing but your R3, that is known as V3, no problem. So what is R3? It consists of all three dimensional tuples. So it consists of A1, A2, A3 such that this A1, A2, A3 belongs to real number, right? So we have a vector space. So we have a V. So V to be equal to R3, and then we have a field. This field can be anything. It can be anything. And I'm taking a subset W. I'm taking subset W. W consists of all those coordinates where your third dimension is 0. Sorry, third coordinate is 0. X, Y, Z, right? So W consists of all those A1, A2, comma 0. This A1 and A2 belongs to real number. So we need to show this is a subset. This is a subset surely, right? Because R3 is A1, A2, A3. A1, A2, A3 can be 0 or non-zero. This surely W is subset of A3, right? Because every element of W is also an element of V. Every element of that is also an element of V. So obviously it will be a subset. Now we need to prove this is subspace, right? For subspace, what I need to do? You take two elements, UV in W. Then you need to show U plus V is also in W, right? So we will show this subspace. So let us take two element UV in W. So every element U is of the form, let us say U is A1, A2, 0. And let us take V to be equal to some V1, V2, 0. Because every element is a triads here, triplets. So a1, a2, 0. Every element will be like 1, 2, 0, 3, 2, 0, minus 5, 4, 0. Third quantity will be 0. So let us take two element. Now we will show that u plus v is also in. What is u plus v? So u plus v is a1, a2, 0. See here a1 and a2 are real number. b1 and b2 are real number. Now what is u plus v? So it will be b1, b2, 0. So which is nothing but a1 plus b1, comma a2 plus b2, comma 0 plus 0. A1 plus b1 is a real number. A2 plus b2 is a real number, and this is 0. Which is this element will also be in W, right? See, W consists of all those triplets where first quadrant is real number, second quadrant is real number, third is 0. Obviously, A1, B1 are real number. This will be real number, this will be real number, and this will be some 0. See, for example, you take 1, 2, 0. You take 3, 4, 0. What is added? It will be 4, 6, 0, which is again an element of W. So obviously it will be W. So therefore it belongs to W. Now let us take alpha. Alpha belongs to field. Alpha belongs to field. And let us take U in W. Right. So let us take U to be equal to sum A1, A2, 0. Now what is alpha times U? So alpha times A1, A2, 0. So which is alpha A1, alpha A2, 0. Right. Which is again alpha A1 is a real number, alpha A2 is a real number, alpha times 0 is always 0. So which is again an element of W. So you take one alpha and you take an element W here, you multiply here, the resulting element will also be in W because it is also of the form A1, A2, 0, where A1 is a real number. So therefore, so you can see that for U comma V belongs to W, U plus V belongs to W, this is true. And for alpha belongs to field, U belongs to W, alpha U is also in W. So it satisfies both the condition. So therefore W is a subspace. So now at the beginning it is a subset only. A subset will be a subspace. You take two element in W, U plus V is also be in W. You take alpha in field, then alpha into U. That element should also be in W, which is again true. So therefore it is a subspace. Okay. Prove that the set of all solutions a comma b comma c of the equation a plus b plus 2c is equal to 0 the subspace of vector space V3 of R. Okay. So here you can see V is again R3. So V is again R3 and your field is real number, right? And your field is real number. What is your V? So your V is R3. So which consists of all those triplet A comma B comma C or A1, A2, A3. And it's not a problem. Where A comma B comma C belongs to real number. Now what is your W? W consists of all those solutions of A plus 2B plus 2C is 0. So W consists of all those solutions of this equation. For example, 0, 0, 0. It's a solution, right? And 1, 1, -1. It's a solution, right? 1, 1, -1 because 1 plus 1 is 2, 2 into -2 is 0. So you collect all those triplets that satisfies this equation. So W consists of all those A comma B comma C that satisfies A plus B plus 2C is 0. Now we need to show this is truly subspace, sorry, subset, right? Because you can see 1, 1, -1 will be in W. That is also an element of B. Every element of this solution is it's an element of R3. That is obviously a subset. Now we will show that it is subspace. We show it is a subspace. So you take two element. You take two element in W. Let us take you two element in W. See how the element is. So I'm taking two solutions, right? Because every element is a solution of that equation. So let us take U to be equal to some A1, B1, C1 such that A1 plus B1 plus 2C1 is 0. That is I'm taking one solution. Let us call that as A1, B1, C1. That triplet satisfies this condition. And let us take V to be equal to A2, B2, C2 such that A2 plus B2 plus 2C2 is 0. I'm taking two solutions. Now I need to show U plus B is also in U plus B is also a solution, right? If U is a solution, B is a solution, I need to show U plus B is also a solution. If I say U plus B is also a solution, then U plus B will be in W. Now what is U plus B? Now U plus B is A1 plus A2, B1 plus B2, C1 plus C2. Now I need to show this is also a solution. So I need to show uh, A plus B plus 2C is equal to 0. So I need to show this belongs to W. That means I need to show this triplet is also a solution. This tuple is also a solution. So let us try to find that value. Now, now what is A1 plus A2 plus B1 plus B2 plus 2 times C1 plus C2? If I say this is equal to 0, can I say that this belongs to W? See, this is one. You see, this is one element. This element plus this element plus 2 times this element. If this is 0, then this element will be in W because this is our solution. Let us try to find this value. Now, this is, can I write this as A1 plus B1 plus 2C1 plus A2 plus B2 plus 2C2? Can I write like this? I'm just reordering, right? Just reordering. And we know this is equal to 0 because I know I've assumed that I have taken UV in W. This is 0, this is 0. So therefore, this is a solution. So this implies U plus B belongs to W. So if U and B are two solutions, then U plus B is also a solution, right? Yes. Now I need to do the second thing. So let alpha belongs to field and let us take U belongs to W. Let us take U to be sum A1, B1, C1 such that A1 plus B1 plus 2C1 is 0 because I have taken one solution. Now I need to show alpha U is also a solution, right? Alpha U is also a solution. What is alpha U? Alpha times A1, comma, alpha times B1, comma, alpha times C1. So if I show this pair also satisfies this equation, then I say this is also a solution. Let us try to find this value. Alpha A1 plus alpha B1 plus 2 times alpha C1. Let us take alpha common. So we will have A1 plus B1 plus 2C1 and we know this belongs to W. Therefore this alpha into 0 which is also 0. So therefore alpha U is also in W. So therefore it is a subspace. Therefore it is a subspace, right? Very easy. Okay. So that the set W of the elements of the vector space of the form where x comma y belongs to a subspace of V3 of R. Okay. So here your V is R3 and your field is real number, right? Your field is real number. I'm taking a subset of W and W consists of element of this form only. Let us take x and y to be equal to 1 1. Then what this element is? 3 comma 1 comma 2. 3 comma 1 comma 2. Let us take x to be 1, y to be 0. There will be 1 comma 0 comma minus 1. So obviously all the elements, if you vary xy to be real number, this element all will be a subset of V, subset of R3. Now we need to put the subspace also, right? Okay, so what is your V now? So V consists of R3. So R3 is all those A1, A2, A3 such that this A1, A2, A3 belongs to real number. See, since here is X, Y, Z, okay, no problem. What is your W? W consists of all elements of the form x plus 2y, y minus x plus 3y, this xy belongs to real number. Now let us take two element uv in W. We'll show that u plus v is also in W. So we'll show you take two element uv in W. So let us take uv in W. So u will be of this form. Let us call it as x1 plus 2y1, y1 minus x1 plus 3 times y1. V is equal to x2 plus 2y2, y2 minus x2 plus 3y2. I've taken two element in W and we know every element of W is of the form this. I need to show u plus v is also in W, right? Now what is u plus v? So u plus v is x1 plus 2y1. Let us add this directly, right? So it will be x1 plus x2 plus 2 times y1 plus y2, y1 plus y2 minus x1 minus x2 plus 3 times y1 plus y2, which is again of the same format, right? X plus 2y. See, let us call this as some p. So p plus 2q, q, let us take minus outside here, minus p plus 3q, where p is x1 plus x2, q is y1 plus y2. This is again a real number, right? Which is again a real number. So which is again of the same form. So this belongs to W because it is also of the form p plus 2q. See, p can be any real number. X1 plus x2 can be any real number. Real number plus 2 times real number. Real number minus real number plus 3 times real number. Same pattern. So u plus v is in W. Now alpha u. So alpha times, let us take u to be some x1 plus 2y1, x1 plus 2y1, y1, y1 minus x1 plus 3y1. Now I need to prove which is again of the form, which is also belongs to W, right? So this is alpha x1 plus 2 alpha y1 minus alpha x1 plus 3 alpha y1. This is a real number. So real number plus 2 times real number. This real number, 2 times real number. This again belongs to W. So therefore it is a subspace. Therefore it is a subspace. Okay. Now we move on to fourth problem. So fourth problem has 5 subdivisions here. Fourth problem has 5 subdivisions here. I think it is not visible. Yes, I think it is visible now, right? Okay. So which of the following sets of vectors are subspace of Rn? So we have 5 subdivisions here in this problem. Which of the following, it is visible, right? Which are the following sets of vectors in Rn are subspace of Rn? So your V is Rn. So your V is Rn and your field is Wall set of a subspace of Rn. Let us take C to be equal to R, right, regardless of R. Now, what is your V? So V consists of Rn. So n can be anything. It is greater than 3. It can be 3 tuple, 4 tuple, 5 tuple. It can be any n tuple. So your V consists of all those. Sorry. So V consists of A1, A2, A3 and so on up to An, and this A1, A2 and so on up to An belongs to real number. So this is your n tuple. Now first first let us take W1. Let us take W1. So W1 consists of all alpha. So W1 consists of all those alphas, all those tuples such that the first coordinate is less than or equal to 0. See, proving subspace, you have to prove two things. But to disprove, very easy. Giving counter example is more than enough. So what I will do is I'll give you counter example. For to be a subspace, the sum has to be in W and alpha times U has to be in W. And I'll give you a counter example, right? Uh, so let us take one element. Let us take one element U belongs to W. Can you give me an example of one element in U? Let us take this as minus 4 comma 1 comma 3 and so on. Let us take any coordinate, right? Let us take any coordinate. See, it can be any coordinate. Let us take or let us say that your first coordinate is negative and all other are anything, and all other are anything. Right, I'm just taking first coordinate to be negative. This element will be in W, right? Because A1 is less than or equal to 0. Now let us take alpha to be minus 1 because alpha belongs to field and your field is real number. Now what is alpha U? Alpha U is 4 comma minus A2 comma minus A3 comma up to minus AN. This whether this element belongs to W? Yes or no? No, right? Why? Because your first coordinate becomes positive now. So U consists of all those elements only if this is negative. I'm taking one element in U and I'm taking an alpha. Counter example only I need to be. It has to be true for all alpha U. I given you one U in W and one alpha in field such that alpha U does not belongs to W. Why? Because this 4 is less. If the first element is less than or equal to 0 only, it will be there. So therefore, it is not a subspace. Not a subspace. So not a subspace proving is very easy. We are also clear counter example that you will get very easily when you have good clarity. Okay. Now second, all alpha such that A1 is an integer. Okay. So what is second is let us call that as W2. So W consists of all those tuples. See, all are different problems, right? Different problems. Here A1 is an integer. A1 belongs to integer. Again, the same second condition will fail, right? So let us take an element U in W2. Let us take U to be 2 comma. Let us take other elements to be anything, right? Now let us take alpha belongs to field which is here is real number. Let us take alpha to be equal to uh, let us take alpha to be equal to some 2 by 3, some 2 by 3, because 2 by 3 belongs to real number, right? Now what is alpha times U? So 2 by 3 times 2 comma A2 comma A3 and so on up to AN. So this will be 4 by 3 some A2 A3 and so on up to AN, right? This will be some real number, right? It will be some real number, but this does not belongs to W because this element this element is not an integer, right? Whenever your A1 is integer, it will be in W. So here I have given you one example of an element U in W and alpha in field, but alpha F is not in W. So therefore, it is not a subspace. Yes. Now let us take the third problem. So what is W3? W3 consists of all those alphas. A1 plus 4 A3 is 0. So it consists of A1, A2, A3 and so on up to AN, such that A1 plus 4 times A3 is 0. That is, you have to add this with 4 times A3, it has to be 0. A1 plus 4 A3 is 0. Now let us take two element in W3. Let us take U to be A1, A2, A3. I'm taking one tuple, but this U belongs to W3. That means A1 plus 4 times A3 is 0. Let us take B to be some another tuple B1, B2, B3 and so on up to Bn, such that B1 plus 4 times B3 is 0. Right? I've taken two element UV in W. Now I need to prove U plus V is in W. Right? Now what is U plus V? Now what is U plus V? A1 plus B1, A2 plus B2 and so on up to what is third element? Third element is A3 plus B3 and so on up to AN plus BN. Now I need to prove this element belongs to W. That means I need to prove this element plus 4 times this element if this is 0. See, an element, a tuple will be in this W3 if A1 plus 4 times A3 is 0. Now what is A1 plus 4 times A3? See, this is the first element, this is the third element. So this plus 4 times has to be 0. Now this is equal to, can I write like this as, can I write this as A1 plus 4 times A3, B1 plus 4 times B3. Can I write like this and this reordering? We know U belongs to V, W3. B belongs to W3. So therefore these two are 0. So this is nothing but 0 plus 0. So therefore this element plus 4 times element is 0. That means this element belongs to W. Is it clear? So whenever your first coordinate plus 4 times third coordinate is 0, you take two elements like that, then the sum will also be in W. Yes. Now we need to prove that alpha U is also in W, right? We need to prove alpha U is also in W. So let us take alpha in field. Let us take alpha in field. Let us take one element U in W. Let us take U to be A1, A2, A3 and so on up to AN, such that A1 plus 4 times A3 is 0. This is true because we can U in W. Now we will prove that alpha times U is in W. Now what is alpha U? Alpha A1, alpha A2 and so on up to alpha AN. This element will be in W if alpha times A1 plus 4 times alpha A3. Let us try to find this value. If this is equal to 0 means it will be in W, right? Because first coordinate plus the 4 times third coordinate. Now let us take alpha outside. So you will have A1 plus 4A3, which is alpha into 0 because this element is 0, this is 0. So therefore alpha U also, this element plus this third element is 0. So therefore alpha U belongs to W. So therefore W3 is a subspace. W3 is a subspace, right? Okay, let us take two elements U3, W3 because I'm named as W3. I'm named as W3. W3. So W3 is subspace. Now we'll move on to fourth. Now what is fourth? You are taking all those alpha such that you are taking all those alpha. Uh, you are taking all those alpha such that A2 is A1 square. A2 is A1 square. So W4 consists of all those tuples such that A2 is A1 square, right? A2 is A1 square. The A2 is nothing but A1 square. Now let us take two element Let us take two element UV in W4. Can you give me an example of one element in W4? Let us take 1, 1. It can be anything, A4 and so on up to A. You can see 1 square A2 is same as A1 square. A2 is same as A1 square. Let us take B to be equal to 9, 3, A3, A4 and so on up to AN. See this A1, A3, A3, A4, AN all are real number. All are real number. This belongs to W4, this belongs to W4 because A2, 3 is A1 square. 3 is nothing but A1 square, sorry, A1 square is A2 is A1 square, right? A2 is A1 square, yes. So U belongs to W4, B belongs to W4. But U plus B, what is U plus B? 4, comma 10, comma some, let us say it is some instead of A3 plus A3, let us say it is some P, comma Q, comma and so on up to AN. Now this does not belongs to W4. Why? Because 10 is not equal to 4 square, right? Because A2 has to be square of A1. A1 square is A2. So I taken two element in W4, but the sum is not in W4. So therefore it is not a subspace. Now we'll move on to fifth. So what is W5? So W5 consists of A1 plus 3A2 is A3. So this is same as second one. You can do this, it will be subspace. A1 plus 3A2, A1, A2 and so on up to AN. A1 plus 3 times A2 is A3. See, proceed as proceed like W3. It is a subspace, right? Take this exercise. So we'll move on to next problem. So yes. Now let V be the real vector space of all functions from R to R. Which are the following are functions? Which are the following sets of functions are subspace of V? Okay. So your V consists of all those functions. We already proved this is a vector space over a field F which is a real number. V consists of all those functions. In first subdivision, I am collecting all those functions such that f of 0 is equal to f of 1. So you input 0, input 1. Both the output has to be same. So you collect all those functions. Is that a subspace? Surely it will be a subspace. Sorry, it is subset. So what is your W1? So W1 consists of all those functions such that f of 0 is same as f of 1. You collect all those functions like this. Is it a subspace? See, instead of proving two things, u v belongs to w, u plus v belongs to w, alpha u belongs to w, we can also prove one thing which is alpha u plus beta v in w. Okay, so let us take uv in w1. Let us take two functions. Let us take u to be some function f, u is some function f such that f of 0 is equal to f of 1. Let us take v to be another function g such that g of 0 is equal to g of 1. And taken two functions f g. Now what is u plus v? So which is nothing but f plus g. Now we need to prove f plus g of 0 is same as f plus g of 1. For this function also f plus g of 0 Now what is f plus g of 0? Now what is f plus g of 0? This is same as f of 0 plus g of 0, so which is 0 plus 0, because f of I need to prove f plus g of 0 is equal to f plus g of 1. Okay, we'll prove like this. This is f of 0 plus g of 0, and we know f of 0 is same as f of 1 and g of 0 is same as g of 1, so which is f plus g of 1. So f plus g of 0, see, we have a new function f plus g, which is some function. For that function also, if your input is 0 and if your input is 1, both outputs are same. Therefore, sum is in u. And now alpha times f plus g of 0 is same as alpha times f of 0 plus alpha times g of 0. Now alpha times f of 0 is same as f of 1, g of 0 is same as g of 1 by assumption. If we take alpha outside, it is nothing but f plus g of 1. So alpha times alpha f plus g of 0 is equal to alpha times f plus g of 1. So therefore, sum is also in u and the alpha u is also in u. So therefore, it is a subspace. It is a subspace. Now second, W2 consists of all those functions such that f of minus 1 is 0. F of minus 1 is 0. Let us take two element in W2. Let us take two element in W2. That is, every element is a function here. So f of minus 1 is 0, g of minus 1 is 0. I'm taking two functions in W2, so therefore both the input value of minus 1 will be 0. Now what is f plus g of minus 1? So it is nothing but f of minus 1 plus g of minus 1, so which is 0 plus 0, which is 0. So therefore f plus g is also in W2, because for f plus g also, if your input is minus 1, the output is 0. Now alpha times f. Actually here we don't need f plus g, right? Here we don't need f plus g, because here one element is, you don't need f plus g here, because you have to take one element in u, right? Let us take the element to be some f. Let us take alpha times, you take one element f, alpha times f. So alpha times f of x. Now what is alpha times f of 0 is same as alpha times f of 1. So obviously it will be in W, right? You take one element in f and you take one element in field, alpha u has to be in this. So what is alpha times f of x? So what is alpha times f of x? Alpha times f of 0. And we know this is same as f of 0 is equal to f of 1, because f belongs to g. So therefore, alpha times f of u is equal to alpha times f of 1. That means f of 0 is equal to f of 1. So again, it will be in W. Now, what is alpha times f of x? So alpha times f of minus 1, which is again 0, because f of minus 1 is 0. So alpha f belongs to W2. So therefore, it is a subspace. Therefore, it is a subspace. Now all f such that f is continuous. Again, it is the subspace, right? Already we have shown that set of all continuous functions is a vector space, and also we have shown that it is the vector space also. All f such that f is continuous. Third, W3 consists of all those f such that f is continuous. Now you take two element in W3. Now what about f plus g? It will be in W3, right? Because f is continuous, g is continuous, and we know sum of two continuous function is continuous. Sum of two continuous function, sum of two continuous function is continuous. And what is alpha f? This also in W3, because alpha f is also continuous. Because if f is continuous, alpha is nothing but scalar multiple. So again, alpha f is continuous. So therefore, W3 is a subspace. Fourth, now W4 consists of all those functions f such that f of 3 is 1 plus f of minus pi. Now you have to this is need not be, right? So you just apply that the sum function need not be in W. So you take two element you take two element in W4. So that means f of 3 is equal to 1 plus f of minus pi, and the g of 3 is same. You have two different functions, and those will that will satisfy this property. Now whether f plus g of f plus g of 3 or f plus g of 3, f plus g of 3 is what? 1 plus f plus g of minus pi. Need not be, right? Need not be. You give me a counter example. You in the after this video, you give me a counter example. You tell me two function that satisfies, if your input is 3, that is same as 1 plus f of minus pi, and you tell me two distinct function, but your sum function will not satisfy that. It need not be. F plus g of 3 need not be 1 plus f plus g of minus pi. Need not be, right? So it is not a subspace. Now fifth is all f such that f of x square is same as, so W5 consists of all those f such that f of x square is same as f of x whole square. Okay, let's give counter example. Let us take f of x to be equal to 1, and this belongs to W5, right? Because 1 square is same as 1 whole square. You take f of x to be x square. This also belongs to W5, because what is f of x square? It is x power 4. What is f of x whole square? Again, it is x power 4. But g, let us g. But what is f plus g of x? F plus g of x is 1 plus x square, right? Or let us call this as h of x. Let us call this as h of x. H of x is some function. This function will not satisfy this property, right? Now, what is h of x square? What is h of x whole square? H of x square is 1 plus x power 4, and h of x whole square is 1 plus x square whole square. This 1 plus x power 4 plus 2x square, so they are not equal. That means this f plus g does not belongs to W5. So 1 belongs to W5 because f of x square is equal to f of x whole square, and g x square belongs to that function, but your sum function is not in W5. So therefore, not a subspace. See, not a subspace, giving counter example is more than enough. Okay, so as of now, what we did so far is we have introduced the definition of subspace, and then we have seen first exam problem, second problem, third problem. In fourth problem, we have 5 subdivision. In fifth problem, again we have 5 subdivision. Now we'll move on to sixth problem. Is it clear up to now? See, in the first example, your B is Rn, that is in the 5 subdivision problem we had no. And then the second, we have taken B to be set of all functions. Now here B consists of all those 2 by 2 matrices. B consists of all those 2 by 2 matrices. Which are the following which of them are subspace of B? All those matrix A such that A square is A. A square is A means it is idempotent matrix, right? So your B is set of all 2 by 2 matrices. So B is M2 of R, set of all 2 by 2 matrices, and your field is real number. Okay. Your field B is set of all 2 by 2 matrices. It is nothing but M2. Now your field is real number. So B consists of all 2 by 2 matrices. A, B, C, D. This A, B, C, D belongs to real number because your field is R. Now you collect all those matrices A such that A square has to be equal to A. I'm collecting all those matrices such that the square will be equal to A. Surely it will be a subset because it will be that element only. Now we'll show that it is a subspace or not. Let us take two matrices. Let us take two matrices in W1, right? Or let us prove this. See, for subspace, two conditions has to be satisfied, right? Let us take an element A in W1. So let us take A to be 1 0 0 0 1 0 0 0. Now what is this? This belongs to W1. Why? Because what is A square? A square is 1 0 0 0 into 1 0 0 0, which is same as 1 0 0 0. So A square is same as A. A square is same as A, product of matrices. So this will be belongs to W. But let us take some element alpha. Let us call it as some 4 belongs to field. But what is alpha times A? 4 times 1 0 0 0, which is 4 0 0 0. This does not belongs to W1, right? I'm taken one element in W, which is 1 0 0 0. That A square is same as A. I'm taken you take an element alpha from field. This does not belongs to W1 because why? A square is not equal to A. What is 4004 into 4000? It will be 16000. So A square is not equal to A, right? So square, you have to square that matrix, you have to get A again. So therefore it is not a subspace, right? So A square is equal to A is not a subspace. Okay. Because this fails this property. Now for W2 consists of all those matrices A such that A square is 0. Nilpotent. A square is 0. Okay. Let us take two elements in W2. Let us take A to be 0 1 0 0. Let us take B to be 0 1 0 0. Both the element will be in W2. Why? You just find A square, it will be 0. Just find multiply 0 1 0 0 into 0 1 0 0. So this into this 0, this into this 0 0 0. So you can see A and B belongs to W2 because when you square it will be equal to 0. But A plus B will be 0 1 1 0. This does not belongs to W2 because when you square this it will not be 0, right? Because 0 1 1 0 square is not equal to 0 matrix. See, 0 means 0 matrix here. When you square is not in 0 matrix. So therefore it is not a subspace. It is not a subspace, right? It is not a subspace. Is it clear? A square is equal to A fails that second property and the sum function is not here, so not a subspace. All those A such that trace of A is 0. So W3 consists of all those matrix A such that trace of A is 0. So trace is nothing but sum of the element. This is subspace, right? So you take, let us take two element AB in W3. Sorry. You take two element in W3. Now what is A plus B? A plus B will also be in W3. Why? Because trace of A plus B will be same as trace of A plus trace of B, and AB belongs to W3, so trace of A will be 0, trace of B will be 0. So trace of A plus B is also 0, so A plus B belongs to W3. Now alpha times A will also be in W3 because trace of alpha A is same as alpha times trace of A, which is alpha into 0, which is 0, right? So therefore alpha A belongs to W3. See, normal trace property, right? Trace is nothing but sum of diagonal elements. Sum of the diagonal elements, and these are basic properties of trace that you'll come to know in the upcoming classes. Trace of A plus B is same as trace of A plus trace of B, and trace of alpha is same as alpha times trace of A. So therefore, trace of alpha is also 0. That means alpha A will be in W2, and trace of A plus B is 0. So therefore, A plus B will also in 0. Okay. Now what is fourth? Fourth is W4. So W4 consists of all those matrix A whose determinant is 100. All those matrix A whose determinant is 100. So let us take two matrices whose determinant is 100. Use the sum matrix determinant is also 100. Need not be, right. So let us take two matrix AB belongs to W4. Let us take A to be 100, 0, 0. So this belongs to W3 because determinant is 100, right? Determinant is 100 minus 0. Let us take B to be 100, 1, 0, 0. This also belongs to W4, right? Because this also determinant is 0. Now what is A plus B? A plus B is 101, 0, 0, 101. This does not belong to W4 because determinant of A is not equal to 100. So you take two element matrix whose determinant is 100, but the sum matrix determinant is not equal to 100. That means this does not belong to W4, so it is not a subspace. What happens if the determinant of A is 0? You collect all those matrix whose determinant is 0. Is that a subspace? You collect all those matrices whose determinant is 0. So if two determinant is 0, if the sum matrix determinant is also 0, take this exercise. So if the determinant is 0, we call it as singular matrices. These singular matrices is a subspace. This is exercise, right? So whenever I say exercise, give that importance. I'm giving one exercise that is a set of all matrices whose determinant is 0. Is subspace or not? Yes, determinant is 100. If determinant is 0, is subspace or not? Comment after the class in the comment section. Okay. Now what is fifth? Fifth W5. So this consists of all those matrices A such that A is same as A transpose. Which is A is nothing but symmetric matrix, right? A consists of all those symmetric matrices because A is equal to A transpose. So obviously this will be a subspace. So you take two element AB in W5. You take two element AB in W5. So that means A is same as A transpose, B is same as B transpose. Now we need to show A plus B is also in W. So what is A plus B transpose? This is nothing but A transpose plus B transpose. So it is A plus B. So A plus B transpose same as A plus B. So this implies A plus B is also in W5, and also alpha times A transpose is same as alpha times A transpose. It's nothing but alpha times A transpose, which is nothing but alpha A. This again belongs to W5. So therefore it is a subspace. Is it clear? Okay, so I move on to problem number 7. So if a vector space B is set of all real valued continuous function over real numbers, so set of all solutions of the subspace of B. Okay. See, this is an second order differential equations, right? B is set of all, sorry, B is the set of all real valued continuous function. Okay. So B is C of 0 comma 1. Okay, set of all continuous over real. Okay, so B consists of all those continuous functions. Here W is the set of all solutions of differential equation. So W consists of solutions. All those solutions are 2 times d square y by dx square minus 9 times dy by dx plus 2y is 0. See, we have already solved one problem, right? One system of equation solution. So let us take two solution. Let us take two solution y1 and y2 in W. y1 y2 a solution. That means 2 times d square y1 by dx square minus, see, y1 is a function here, plus 2 times y1 equal to 0, and also y2 is also a solution. So 2 times d square y2 by dx square minus 9 times dy2 by dx plus 2 times y2 is 0. Now I need to show that sum is also solution. Okay, I'll prove this in single stroke. Let us prove that alpha times this also belongs to W, right? Instead of proving u plus b, I'll prove this alpha y1 plus beta y2 is also in W. Then I'll show it in subspace, right? Now I need to prove this also solution. Let us to prove this belongs to W. So I need to prove this is a solution. Okay, so let us try to find the value of 2 times d square by dx square of y1 minus 9 times d by dx of alpha y1 plus beta y2 plus 2 times alpha y1 plus beta y2. Let us try to find this value. If this value is 0, then this is a solution, right? That means this belongs to W. Okay. Can I write this as, can I write this as, let us take alpha outside, uh, 2 times d square y1 by dx square minus 9 times dy1 by dx plus 2y1, because this is a linear property, right? Differential operator is a linear operator. So differential operator is a linear operator. Differential is a linear operator. You can always differentiate inside, right? You can always take derivative inside. Plus beta times, let us try to like this as 2 times d square y2 by dx square minus 9 times d y2 by dx plus 2y2, which is nothing but alpha into 0 plus beta into 0, because this is 0, this is 0, right, by assumption. So therefore this also is solution. Alpha y1 plus beta y2 is also a solution. So therefore it is a subspace. Very important problem. So you take two solutions, you need to show this also W. That means you need to show this is a solution. You need to show that is a solution. So instead of y, you place that alpha y1 plus beta y2. If that is equal to 0, then it will be a solution, right? So it is a subspace. Okay. So now we will move on to the next topic, which is theorems on subspace. So we're going to prove 3 theorems now, and then we'll wind off this class. So I'll start rank in the next class, right? We're going to see 3 theorems now. We'll have a 2-minute break and then we'll resume. Yes, so we'll start. So actually there are three theorems on subspace. So I will prove that. We'll start with the first theorem. Theorem 1. The intersection of two subspace is a subspace. That is the first theorem. The union of two subspace, the intersection of any two subspace is also a subspace. The intersection of any two subspaces, the intersection of any two subspaces W1 and W2. The intersection of any two subspaces and W2 of a vector space of a vector space V of F is also a subspace of V of F. Is also a subspace of V of F. Okay, the intersection of any two subspace is also a subspace, right? Is proof. Okay, so we have a set V and then we have a field F. You take two subspace, right? You take two subspace W1 and W2. You take two subspace W1 and W2. The intersection is also a subspace. So I need to show this element, right? This all these elements is also a subspace of V. So this is nothing but what? W1 intersection W2. So I need to prove this is a subspace, right? So let W1 and W2 be two subspace. Let W1 and W2 be two subspace of V. So W1 and W2. So what I need to do is I need to show what we need to show W1 intersection W2 is a subspace, right? So that is to show you take two element in W1 intersection W2. I need to prove alpha x plus beta y is also in W1 and W2, right? Instead of we are taking xy, that is not a problem, right? You take two element xy here. You show that alpha x plus beta y is also in V. Is also in you take two element here. Alpha x plus beta y is also in this set. That means this set is a subspace of V. This is what we need to prove, right? Let us take two element xy in W1 and W2. We need to show alpha x plus beta y is also in V. Let us prove this. Right? Very simple proof. Proving is very, very important, right? If you understand the concept, proving will be very, very easy. Right? I'll prove this. Okay. This is what I need to prove, right? How to prove. Now x comma y belongs to intersection. This implies, can I say x comma y belongs to W1 and x comma y belongs to W2? See, x comma y is in intersection. That means x comma y is also in W, x comma y is also in W2. Obvious. X comma y belongs to W1 and W1 is a subspace. Can I say alpha x plus beta y belongs to W1? Can I say alpha x plus beta y belongs to W2? Because W is a subspace. By definition, if you take any two element, then this combination will always be in W1 because by definition of subspace. Because W1 and W2 are subspace because W1 and W2 are subspace. So by definition, you take any two element in W1, then alpha x plus beta y will be in W1 by definition. And again, if you take any two element in W2, this will be in W2. Now, alpha x plus beta y belongs to W1 as well as alpha x plus beta y W2. Can I say alpha x plus beta y, this element is in W1 as well as this will be in W2? Can I say this element will be in W1 intersection W2? That's it. Proof is over. Very simple, right? So this implies I'm taken two element x comma y in W1 and W2. This one need to prove. This implies W1 intersection W2 is a subspace. Very, very easiest to prove. In this way, you can extend any n numbers also. In this way, you can extend any numbers also. So I'm taking two element. I'm taking two element here. I need to prove alpha x plus beta y is W1 into W2. X comma y belongs to W1. That means alpha x plus beta will be in W1. X comma y belongs to W2. That means alpha x plus beta y will be in W2 because of the subspace. So alpha x plus beta y is in W1 as well as in W2. That means alpha x plus beta y will be in W intersection W2. Where I taken x y in this W1 intersection W2. So therefore it is subspace. Right. Now theorem 2, union of two subspace need not be a subspace. Union of two subspace need not be a subspace, right? Union of two subspace need not be a subspace. Let us prove that. Intersection is always a subspace, right? Intersection is a subspace. You take any two subspace, intersection element is a subspace of V of f, right? Now we will prove that the union of any two subspace, the union of any two subspace W1 and W2, the union of a vector space V of f of a vector space V of f need not be a subspace. Need not be a subspace. The union of the union of two subspace need not be a subspace. Whenever we need to show not, you have to give a counter example, right? Okay. In the previous theorem, we have proved that the intersection of two subspaces is a subspace. Now we will prove that union need not be a subspace. Let us take V and we have a field F. We have a field F. Let us take two subsets, right? W1. Let us take two subsets W2. The last example, we prove that this intersection is subspace. Now we will prove that the union is not a subspace, right? I'll give a counter example. Let us take W1 to be, let us take V to be, let us take V to be equal to R2. Let us take V to be equal to R2. Whenever I need to do not, I'll give a counter example, right? Let us take V to be equal to R2. So your R2 consists of all those pairs x comma y. X comma y belongs to real number. Let us take two subsets of this. Let us take W1 to be all x comma 0. This x belongs to real number. And let us take W2 to be equal to all those 0 comma y such that y belongs to real number. That is, I'm taking W1. See, here W is a subspace, W2 is a subspace. Here W1 is a subspace. Y is a subspace. Why? Because alpha, you take any two element. You take any two element in W. So let us take U to be some x1 comma 0, v to v some x2 comma 0. Now let us prove alpha u plus beta v is also in W. Now what is alpha times u? X1 comma 0 plus beta times x2 comma 0. This is nothing but alpha x1 plus beta x2 comma 0, and this belongs to W 1 because first element is any real number, second is 0. So therefore you take any two element in W, then alpha u plus beta v is also in W. Also W2 is also a subspace. W2 is also a subspace. Why? You take any two element uv in W2. Let us take u to be some 0 comma y1. Let us take v to be some 0 comma y2. Then what is alpha u plus beta v, which is again belongs to W2. This again belongs to W2, right? Because it is also of the form first element will be 0, second element will be, sorry, first element is 0, second is some non-zero real number, any real number. So I have taken one V and I have given you two subspace. So I have proved that W and W2 both are subspace. But now what is W1 union W2? W1 consists of all those pairs whose second coordinate is 0. W2 consists of all those pairs whose first coordinate is 0. So W1 union W2 will be all those x comma 0 union 0 comma y. This x comma y belongs to real number. So your union consists of all those elements. Either first term will be 0 or second will be 0. I think you're getting my point, right? All those x comma y, either first is 0 or second is 0. 2 comma 0 belongs to W and W2. 0 comma 4 this also belongs to this. Now let us take two element in here. Let us take two element here. We need to show it is not a subspace. So let us take two element here. Let us take some p comma q belongs to W1 union W2. Let us take p to be some 2 comma 0. Let us take q to be some 0 comma 3. So both are in W1 union W2. Yes or no? Both are in union because for p your second coordinate is 0 and for q your first is 0. But p plus q is what? 2 comma 3 does not belongs to W1 union W2 because W1 and W2 either consist of first element has to be 0 or second is 0. So I have taken two element here but sum is not here. So therefore W1 union W2 is not a subspace. Very interesting, right? From this counter example, I can say that the union of two subspace need not be a subspace. I have given you one counter example. So that is enough to say in general that the union of two subspace need not be a subspace, right? So your W1 union W2 consists of all elements, either your all pairs, either your first element is 0 or second is 0. You take two elements like that, but your sum need not be, right? So therefore W union W2 is not a subspace. Now the next thing is union will be a subspace when intersection is always a subspace. Union need not be a subspace. Union of two subspace will be a subspace if there is some condition. That is what the next theorem is. Right? The union of two subspace is a subspace. Theorem 3. The union of any two the union of any two subspace W1 and W2 of a vector space of a vector space VF is a subspace if and only if and only if one is contained in the other. That's it. If and only if one is contained in the other. That is what the next theorem is. If and only if one is contained in the other. For the previous example, one is not contained in the other, right? This is different, that is different. Contained means it has to be inside that. Here I'm having all those x comma 0. Here I'm having all those 0 comma 0. It is not contained in this, right? So in that, at this time only it is on a subspace. Now whenever if you have a subspace like one is contained in other, then it will be a subspace. Let us prove this, right? See, if and only if you have to prove in two parts. You have to prove converse also. Okay, so that means you have a vector space B and you have a field F. So you have W1 and W2 has to be inside this. W2 has to be inside this. You can see W2 is contained in W1 or vice versa. W1 can be inside or W2 can be outside. So union of two subspace will be a subspace. In this case, your W1 union W2 will be a subspace. So union of any two subspace is a subspace if and only if one is contained in the other. One is contained in the other. One is contained in the other. Let us prove, right? See, if and only if. You have to assume this, you have to prove this. You have to prove two types, right? Okay. So let us assume that let W1 and W2 be any two subspace. Let W1 and W2 be any two subspace. W1 and W2 be any two subspace. Right? Let us assume W1 is contained in W2 or W2 is contained in W1. Let us assume this. That is, one is contained in other. What we need to prove? What we need to prove? I need to prove that W1 union W2 is a subspace. This is what I need to prove, right? If one is contained in other, I need to prove the subspace. If and only means you have to assume the contrary. Conversely, also you need to prove that I will prove, right? First, we will assume that. Either W1 is contained in W2 or W2 is contained in W1. And already we know W and W2 both are subspace. This is very simple, right? Now, if W1 is contained in W2, let us say diagram is like this, right? You have B, you have two sets. W1 is contained in W2, right? W1 is contained in W2. This implies what is W1 union W2? It is same as W2, yes or no? When you union W and W2, it is same as W2, right? If W2 is contained in W1, if W2 is contained in W1, then your W1 union W2 is same as W1, yes or no? See, there are two possibilities, or like, or if this happens, then this happens. This is a subspace. Why? Because we know that W1 and W2 are subspace. So therefore, this also has to be a subspace because both are equal, right? This also has to be a subspace. And we know this is a subspace. This is a subspace. So this also has to be a subspace. So this implies what I can say. So this implies W1 union W2 is a subspace. See, already we have assumed that W1, W2, if the union of two subspace, already W1, W2 are subspace. Union will be a subspace if one is contained in the other. So we approved the first part. If W1 is contained in W2, then union will be either equal to W1 or W2, and we know both are subspace. So therefore, obviously this is subspace. Now we'll prove converse. Now we prove converse. Now we prove converse. What is our assumption? Assume that W1 union W2, W1 union W2 is a subspace. What we need to prove? What we need to prove? Either W1 is contained in W2 or W2 is contained in W1. This is what we need to prove, right? Either W1 is contained in W2 or W2 is contained in W1. This is what we need to prove. Okay, so we'll prove this. See here, I need to prove P implies Q, right? I need to prove P implies Q. P implies Q. This is same as proving. This is same as proving not Q implies not P, right? This is same as proving not Q implies not P. So whenever P implies Q, not Q implies not P. So we prove that not Q implies not P. What is not Q? Not is not Q. That is, if W1 is not contained in W2, that is, we prove if W1 is not contained, if W1 is not contained in W2 or W2 is not contained in W1, then W1 union W2 is not a subspace. We will prove this. Proving this is same as proving that not Q implies not P, right? Not Q implies not P. Okay. Now, since W1 is not contained in W2, so that means W1 will be here, W2 will be here, right? This is not contained. Then we can always find one element. Then there exists an element X in W1, but this X does not belongs to W2. Yes or no? Since W1 is not contained in W2, both are different. So you can always find an element X in W1 such that X will be in W1 and that X will not be in W2. And similarly, since W2 is not contained in W1, you can always find one Y. You can always find one Y. Then there exists Y in W2, but this Y does not belongs to W1. You can always find an element XY like this, right? We can always find an element X that will be in W1, but that X does not belongs to W2. And that will be an X and that belongs to W2. Okay. Now, okay. This X will be in W1, but that not in W2. Okay. Let us call this as 1, call this as 2, right? Call this as 1, call this as 2. From 1 and 2, can I say can I say x plus y belongs to W1 union W2? From 1 and 2, can I say, see, x belongs to W1 union W2, y belongs to W1 union W2. So obviously, x plus y belongs to W1 union W2 because it is subspace by assumption, right? X plus y belongs to W1 union W2, right? Okay. Now, x plus y belongs to W1 union W2. X plus y belongs to W1 union W2. That means x plus y belongs to W1 or x plus y belongs to W2. See, very tricky part, very interesting part. X plus y belongs to union. That means x plus y either will be in W1 or W2 or it can be in both also. If x plus y belongs to W1 and we know that already x belongs to W1 and we know that already x belongs to W1 and since W1 is a subspace and since W1 is a subspace, can I say this element will also be in W1 because alpha x plus beta y will be in W1 no, because alpha x plus beta y will be in W1 no, yes or no, alpha x plus beta y will be in W1. So you multiply this by 1, you multiply this by minus 1. So x plus y minus x will be in W1 by this. Yes or no? See this both element in W2. So linear combination will also be in W2. You take alpha to be 1, beta to be minus 1. This implies y belongs to W1, which is a contradiction because y doesn't belongs to W1. Yes or no? Suppose if x plus y belongs to W2 and we know this y also belongs to W2. And similarly, since W2 is a subspace, this will be in W2 because W2 is a subspace. And this implies x belongs to W2, which is a contradiction. We are getting this contradiction because our assumption is wrong. So therefore, if this happens, then this will cannot happen, right? So therefore, W1 union W2 is not a subspace. If that is a subspace, right? Why we are getting this contradiction? Because this is giving you contradiction. This is giving me the contradiction. Why? Because you can see here, I have taken that if x and y are in W2, x plus y is also W2. That means here it is giving that it is a subspace. But if I take this to be a if that happens, it will be a subspace. But if that happens, this will be a contradiction. That means this will not happen. This will not happen, right? If I think when I'm saying this, I think I made some error. Okay, suppose if right, if suppose if this happens, we'll get a contradiction. That means this will not happen. Yes or no? This will not happen means it violates the definition of subspace. So therefore, it is not a subspace. So therefore, W1 union W2 is not a subspace because if you take two element in here, x plus y is not here. I think when I'm doing this, I said I think I said I wrong. I said I wrongly. Wrongly I said I think. Sorry. So you take two element in W in W2. If suppose if the sum is also here, then we get a contradiction. That means sum is not an element. That means it is not a subspace. Sum is not a subspace. Is it clear? Suppose if two elements are in W2 and if the sum is also here, then we get a contradiction. That means sum is not there. So that means sum is not there means it is not a subspace. That's it, right? Sorry. Now I think it will be clear. So this is the proof of this theorem, that the union of two subspace will be a subspace if and only if one is contained in the other. If not, it is not a subspace. Right? Yes. So I'll wind up this session. So in the next class, I will start rank of a matrix and homogeneous and non-homogeneous system of linear equations. After that, we'll continue linear dependent, linear independent, basis, dimensions, linear transformations, and so on. Right. So I think there will be no doubt. So thank you. We'll see in the next class. Right. Thank you.